So hello and welcome class. So this is fluid mechanics. Today our topic is on buoyancy. For our learning objectives, at the end of the session, you will be able to first state Archimedes' principle on buoyancy, and then describe Archimedes' principle on buoyancy, and of course to apply Archimedes' principle of buoyancy on problems. So let us have now the principle of Archimedes on buoyancy. A body immersed in a fluid is acted upon by a buoyant force which is equal to the weight of fluid displaced. So basically, we have the concept of buoyant force which refers to the flotation of a body. So this buoyant force is denoted by Fb, is also known as static lift, and the buoyant force acts on the center of gravity of the volume submerged. So the concentration of the buoyant force is on the location BO, or the center of buoyancy, which is the portion of submerged volume. So the formula on the buoyant force is equal to gamma of the fluid times the volume displaced. So it is denoted by F sub B, that is buoyant force. So gamma is the unit weight of the fluid. And then we also have the volume displaced. So the volume displaced is simply the submerged volume of the body. So if we're going to investigate the units, gamma is in terms of kilonewton per cubic meter in SI, and our volume is in terms of cubic meter. While in that of English system, we have PCF, or pounds per cubic feet, and the volume is in cubic feet. So of course, that would yield to a force unit kilonewton, and for English system, will yield to a force unit of pounds. Now this concept is not different from the concept of the unit weight is equal to weight all over volume. If the weight of the body exceeds the amount of the static lift, the body sinks unless external forces is applied to the body. Of course, this excess weight is what we call the apparent weight, or denoted by Wb prime. And our weight is denoted by Wb minus Fb. So that is the apparent weight which causes the sinking of a certain body. So Fb is the buoyant force, Wb prime is the apparent weight, and then Vd is the volume displaced. So perhaps we can ask the question, which bodies are subject for floating? So our first criteria is the specific gravity. So bodies with specific gravity less than the specific gravity of the liquid involved. So another question is, by how many percent should these bodies be submerged? Of course, if we have to investigate the equilibrium equation on the vertical, equating it to 0, we say that the weight is being countered by the buoyant force. So that causes the flotation of a certain object. Now, the weight to gamma volume. Of course, gamma here refers to the unit weight of the material. Of course, we are concerned with the total volume of that object. While on the right-hand side of the equation, we have the gamma of the fluid involved times the volume submerged. So it should be noted here that the volume submerged is a partial volume of that of the total volume. So therefore, the volume could be partially submerged. So if we are going to solve for the submerged volume by manipulation, we can have the ratio of the unit weight of the material to that of the unit weight of the fluid times the total volume. Now, since this expression is in terms of percentage, noting that the gamma of the material is less than the gamma fluid for a flotation to occur, we can get that percentage of submergence of the total volume. Now, if we expand the formula of the gamma of the material, it could be expressed by the formula coming from the specific gravity. So remember that the specific gravity is the ratio of the gamma of the material all over the gamma of the standard substance, which is water. So on the numerator, we can see here that gamma involved here is the gamma of water because that is the standard substance. So the standard substance would be common to the numerator and the denominator, only that they vary from their corresponding specific gravity. Hence, from this, we can determine the percentage of the total volume using the specific gravity. In here, if we want to express V submerged or the total volume in terms of the area, we can simply write the volume is equal to area times its length, similarly to that of the total volume. So in here, we can cancel actually gamma, and we can just concentrate to the ratio of the specific gravity of the material to that of the specific gravity of the fluid. So we can also remove that into this equation and cancel the length. Of course, that would be vanished in the equation. So in short, we can also use that area submerged, or the submerged area here, is equal to the ratio of the specific gravity of material to that of the fluid times the total area. So let us apply those principles on problems. So on this problem, we are going to determine the depth of flotation of the following. So first, a scow in the shape of a regular parallel tip, 10 meter long, 5 meter wide, weighing 400 kilonewton and placed in seawater of gamma 10.10 kilonewton per cubic meter. On the second condition, we are going to determine the depth of flotation of a log that is having a specific gravity of 0.8 in the shape of a circular cylinder. So the length here is 4 meters and the diameter is 60 centimeters. So this log will be placed in fresh water. On the third requirement, we are going to determine the depth of flotation of a spherical ball having a specific gravity of 5, having a diameter of 10 centimeters, and placed in a body of mercury with specific gravity of 13.6. So in a short while, you can see here what is meant by the depth of flotation. So for the first condition, on a scow in the shape of a regular parallel tip, as a solution, of course, we are going to have the liquid surface. The liquid surface is actually the seawater. And then this is a rectangular parallel tip seen from its width, of course, along its length, that is 10 meters, and the width is 5 meters. So this parallel tip will be placed on the surface of the seawater. So placing that, having our illustration facing the width, this is what we call the draft or the depth of flotation. So the center of gravity of the submerged portion, here we have the buoyant force. So this is the location of our buoyant force. So the center of gravity of the submerged portion will be FB, and then this one is the center of gravity of the whole volume. Of course, this location is BO, and this location is G, or the center of gravity. On the center of gravity lies the weight, which is equal to 400 kilonewton according to the problem. So we use the equilibrium equation along the vertical. We can say that the weight is equal to the buoyant force. So we substitute the weight of 400 and then substitute the formula for the buoyant force, which is the gamma fluid times the volume submerged. So from here, we can substitute the value of the gamma of the fluid, which is seawater, multiplied by the volume. So in here, the volume is 5 by 10 by the draft. So as we can see, the volume involved here is concerned only on the submerged portion of this rectangular parallel tip. That is why the height here is D. So solving for D in the equation, we can get the value of 0.79 meter. So moving on to the next, determine the depth of flotation of a log. Okay, so it has its corresponding specific gravity. As a solution, of course, we draw the liquid surface and then the object. So this is the log, and of course, it is to be placed in a fresh water with gamma of 9.81 kilonewton per cubic meter. Now this log has a 4 meter length and 0.6 meter, or that is 60 centimeter in diameter. Of course, for consistency, we use the same unit in meters. So again, this round log will be placed on the fresh water. Of course, we should note what would be the percentage of submergence here, because we have a definite dimensions for the object. So we use the formula that was derived a while ago, that the area submerged is equal to the ratio of the specific gravity of the material to that of the fluid. Multiply that by the area total. Hence, S for the log is 0.8 and specific gravity for water is 1. If we compute that, it is obvious that we have 0.8, or that is 80% of the total area. So that when we place this log into this liquid, we can now understand that more of the volume is submerged. Now this is what we are trying to obtain here, the depth of flotation. So of course, this log lies the point of origin at the same time the center of gravity. And on the center of gravity lies the weight. And of course, the center of gravity of the submerged portion is BO, or the center of buoyancy. So remember that the, the buoyant force is always going up, because that is what we call uplift force. So it is denoted by FB. And then of course, we need to project a line tangent to the water level so that we can relate the radius to that of the diameter. So here how it goes. So of course, our purpose in constructing this red line, connecting the point of tangency of the water on both ends to that of the point of origin of our log, for us to create an angle theta. So why do we need to form an angle theta? Because we can form a right triangle out of that, and the half of it is theta all over 2. So of course, we are going to utilize this triangle. So basically, that dimension hypotenuse is the radius on the illustration. So this angle is theta all over 2, as denoted in our free body diagram. So let us denote this dimension as y. Remember that y is parallel to that of the unknown graph, so that we can relate the three variables here by the cosine function. So in here, from the relationship, we can write cosine theta all over 2 is equal to y all over r. Hence, by cross multiplication, y is equal to r cosine theta all over 2. So this is the dimension. So see here in the figure, that is part of the graph. And the rest would be the radius. Okay? So that is r cosine theta all over 2. And then the rest would be r. So therefore, the graph can now be expressed in terms of a radius and an angle. So r cosine theta all over 2 plus r will be the graph, or the unknown graph here. Now, if we take a look on the figure, it is much easier to consider a certain area not submerged. Why? Because it is part of a certain sector, and that sector has its corresponding angle that was established, and actually that is our theta. So our focus in here is not on the graph or the submerged portion, but the area not submerged, or the portion that is not submerged in that fresh water. Why? Again, it is much convenient to solve for that sector because we have an angle theta, and that portion portion is the excess of 80% of the total area. So we know here that submerged portion is 80% of the total area, and the area which is not submerged would be the excess, and that is 0.2 or 20% of the total area. So writing now the area not submerged, we can equate that by pi r squared times theta all over 360, or the sector itself. Okay, so this is the sector or a portion of a circle. So we can see that the formula is just the area of a full circle multiplied by the percentage of the angle. So in this one, we have angle theta all over the whole 360 degrees. So we less the triangle, okay, we less at a certain triangle here, and apply the Caesar formula for triangle. That is 1/2 r times r, or that will become r squared, times sine of theta. So remember that the Caesar formula involves two adjacent sides with the involved angle. So we further expand our formula by substituting the left-hand side of the equation, which we know that that is 20% of the total volume. I mean the total area. So 20% of pi r squared equal to, we have the same right hand side of the equation. So we can calculate the left hand side equal to 0.0565 equal to the same expressions on the right hand side, and here we can use our trial and error method or by calculator using the sheep solve method. We can get a value of an angle 121 degrees. So if we know the angle, of course, we can now solve for the graph. Referring back to the figure, graph is equal to r plus r cosine theta all over 2. So we simply substitute the radius of 0.3 as well as the angle 121 degrees. We can now get the graph equal to 0.4476 meters. So this is the vertical height which is submerged in water, fresh water. Okay, so moving on to the next problem. So this time, let us try a spherical ball and submerged or placed in a body of mercury. So this spherical ball is 10 centimeters in diameter. So as a solution, again, we establish the liquid surface, and then this is the spherical ball. So this is a 3D, and Hg or mercury is having specific gravity of 13.6. Now this sphere has 0.1 meter diameter, and to be placed on this body of mercury, of course, we should know how many percentage is submerged here, since we have a definite dimension of the sphere. So that is one thing to note. Class, if there will be a definite dimension of your object to be submerged in a certain liquid, let us determine how many percentage is submerged. So now using the formula, the submerged volume times the ratio of its specific gravity of the material to that of the fluid, we can substitute the S of material to be 5 all over the S of the fluid, 13.6. We can arrive at 36% of the total volume. So the purpose here is to have an appropriate illustration wherein only 36% is submerged in that mercury. So this is the graph. Of course, we have the center of gravity wherein weight is concentrated in, and the center of buoyancy wherein the upward force, buoyant force is concentrated. So if we project the line of the liquid to the point of tangency of the sphere to that of the point of origin of the sphere, of course this is a 3D, we can observe that this is 36% of the total volume. At the same time, this shape is what we call the frustum of a sphere, which is equal to if we have a sphere here, of course this sphere is a 3D, and only a portion of it with a certain height is considered. That is what we call the frustum. Of course, this is the center. So from the center, we have the 3D radius of this sphere. The formula is pi h squared, or the height of the frustum, multiplied by 3r radius less h. So from that, we can now have the volume submerged, because the volume submerged is the frustum itself. So the volume submerged using that formula. So the height of the frustum here is d. So we just have to replace the general formula with d, replacing h with d. So we can write pi d squared all over 3 multiplied by 3r minus d. And that the volume submerged is 36% of the total volume. Now the formula for the total volume of a sphere is equal to 4/3 pi r cubed. So we enclose that, and then going to the right hand side of the equation, we have pi d squared all over 3 multiplied by 3r minus d. So of course, we can get the numerical value by initially substituting the radius of 0.05, or that is half of 10 centimeters. So we equate this by the right hand side of the equation, substituting the known values, the radius, which is 0.05. So we get the numerical value of the left hand side of the equation, equating it to the right hand side of the equation. Pi all over 3, by the way, is 1.047. Of course, 1.047 will be a divisor to 1.88. So 1.88 times 10 raised to negative 4 divided by 1.047, that is 1.795 times 10 raised to negative 4. Equate that to the distribution of D. So 5.05 times 3, that is 0.15, multiplied by D squared. And then the next term, or the second term, will be D times D squared, that is D cubed. So in here, we are dealing with a third degree equation. Of course, we can utilize the Newton's approximation on that equation to come up with the roots of D. So the first root is equal to 0.40. Practically, that would exceed the total diameter of our sphere. That is why it's not the root we are trying to obtain. So the second root is a negative value, of course, that could be neglected. And the third root is 0.0404, which is practically correct because it is less than 0.1 meter. So this will be the answer to this problem. By the way, aside from the method of Newton, we can also directly calculate that in our calculator. We can also have a trial and error. So the next problem refers to an iceberg having a gamma of 9 kilonewton per cubic meter. It floats in seawater whose gamma is 10 kilonewton per cubic meter. If 3000 cubic meter is above the water surface, what is the total volume of the iceberg? So first things first, we need to draw or illustrate the problem. As a solution, as usual, we place the liquid surface and then note our involved liquid and its unit weight, that is 10 kilonewton per cubic meter. So in this portion, the center of buoyancy is BO, wherein the buoyant force is concentrated. With reference to the total volume, we have the center of gravity G, which our weight is concentrated. So in here, this is the exposed portion because according to the problem, the exposed portion is actually 3000 cubic meter. So it says here that if 3000 cubic meter is above the water surface, so having that one, we can name the submerged portion as the difference between the total volume and the portion above the liquid surface. So therefore, that submerged part is the total volume minus 3000. Now, we use the equilibrium equation along the vertical, wherein W will be equal to the buoyant force. So the weight is the iceberg itself times total volume. Gamma of iceberg times the total volume. That is equal to the gamma of the seawater times the volume submerged, according to Archimedes' principle. So we can substitute the values. Iceberg unit weight is 9, okay, times the total volume. equal to the unit weight of seawater is 10 kilonewton per cubic meter times the submerged volume is named to be the total volume minus 3,000. So notice that the equation is only having a single unknown. We can manipulate that and solve for the total volume that is equal to 30,000 cubic meter. So this will be the answer to this problem. So at this point, let us have a recap because all of these principles were applied in those initial problems. So remember here that buoyant force is always going upwards, and the buoyant force is concentrated on the center of buoyancy denoted by B. So in simple problems of buoyancy, we always equate weight is equal to the buoyant force. So that's it for this session, and we are going to continue with the next session with more problems. Thank you.